So I figured when we want to start this unit, we're looking at 3 types of waves. All right. So we've already done transverse waves that go up and down, longitudinal waves, which are pressure waves. Light is a third and completely different type of wave called electromagnetic. And an electromagnetic wave is a wave that doesn't need a medium. Right? This is a wave that's made up of perpendicular electro and magnetic fields. So technically, you and I create a type of electromagnetic wave. The heat in our body creates infrared radiation, infrared rays, and those infrared waves come from the electrons moving. They shake up and down. When the electron shakes up and down, that creates this blue electric field, right? When the electron shakes up and down, it creates the blue electric field. But do you remember, and this is a stretch, in the magnetism unit, that electricity can create magnetism? Any moving electron creates a magnetic field. But also that any moving magnet, you remember we would like spin the magnet and creates electricity? That's actually what light is. You have a moving electron that creates an electric field, which creates a magnetic field. The magnetic field creates an electric field. And they go back and forth, creating each other. And we see these waves as light or feel them as heat. We cook our food with them in a microwave and send cell phone signals to each other in the radio frequency spectrum. These are all waves that are doubly transverse because there's a perpendicular component that's electric. So that's electric field measured in newtons per coulomb. And then there's a magnetic field measured in Tesla. I'm not going to have us draw this wave. Can we agree that drawing this wave would be really difficult? Let's just not. Right? But you should know that it's doubly transverse. It's got transverse bits in both electricity and magnetism. And then they don't need a medium to travel. All the other mechanical waves that we worked with need a medium to travel. Water waves, you can't have water waves without the water. Sound waves, I can't have pressure unless I have a gas for the pressure to travel through. Like I can't have pressure if I have no particles. Right? Earthquake waves need a medium, but any electromagnetic wave does not. And here's actually a really good GIF on why it does not. Right? When light travels through a vacuum, that's this bottom picture. Watch the green. Right? Nothing in the way. And so it travels as fast as it possibly can. It's unimpeded. But adding a medium, adding something in the way, like a bunch of particles, is like adding hurdles. And if you added hurdles to a race, everyone would run slower. Right? Because there's stuff in the way, that actually slows light down. Now there's 2 words on the screen that you might not be familiar with. What is one of them? Photon. A photon is just another word for light. Later in physics, so if you have to retake this in college, if you ever see this again, a photon is a particle of light. So it's another way of saying light. Light is a photon. What's the other word you might not notice or might not know?
Propagation.
Any ideas on what that means? Traveling. So this says the traveling of light through a medium versus the traveling of light through a vacuum. And when I say vacuum in this case, I mean a material or a area of no matter, an area that has no matter or particles or atoms in the way. Okay. So if I put something in the way of light, it actually, and this is kind of weird. So when light goes through glass, like through that window, for instance, every glass molecule that it hits, the light gets absorbed by the glass and then re-emitted. That's why it slows down, because it keeps getting reabsorbed and emitted as it goes through each atom. All right. So if there's nothing in the way, the speed of light is special, right? If there's nothing in the way, the speed of light is so special, it gets its own symbol. It's lowercase c. And that symbol C stands for the speed of light in a vacuum. And I keep calling it the speed of light because that's the name of that constant. It's a constant in the same way that like G 9.8 is a constant. Right? I keep calling it the speed of light, but it's really the speed of any electromagnetic wave. A radio wave, a microwave, an X-ray, they should all travel at this speed. Right? If I put stuff in the way, it's going to slow down. Realistically, if you remember this from the test, I gave you a speed of microwave that was something like 299,700,000 and change. We round it when we use it. So we're going to round that number so you don't have to remember all the little decimals. As light goes through matter, it slows down. But a cool fact about this universe, and it's a thing that we know, but we don't know why it does it. No object made of matter or mass can travel at or above this speed. So there's a limit to physics. At some point, we know that things occur, and we know that they occur in our universe, but we don't know why they occur. So the speed limit to our universe is this number. Nothing can travel faster than this, right? Since nothing can travel faster than this, we can get little tiny particles to get close, but that means there's a limit to how fast we can send information from one place to another. Right? Now, on Earth, that's not a big deal because Earth is small, at least galactically speaking. Right? So my husband is in Afghanistan right now, and when I want to talk to him, I'm going to skip this slide for a sec. Right? Light takes about a fraction of a second to get all the way across the whole planet. Actually, if this were to scale, right, it would take light about 0.13 seconds to go all around the whole circumference of the Earth once. So that means when him and I talk, there's no like time delay. We're so close, at least being on this planet, we're so close on this planet that light only takes a fraction of a second. It completes 7.5 circumferences every second is how fast light is.
How are you talking through light?
Oh, because it's anything. So I could use a radio signal on a cell phone, and that travels at that speed too. So even though this is a picture of light, when you talk on the phone, you're using radio signals to send that message from you, changes to radio to there.
Isn't light faster than the radio signal?
Nope, radio's same speed. All electromagnetic waves travel at this speed.
Oh, got it.
Quinn.
I thought the universe grows faster than light.
The universe grows faster, but not faster than light. Right? So the universe is expanding right now. We think that it's probably going to expand forever. We don't have any indication that it's going to change its behavior. But because the universe is expanding and light has a finite speed, that means that there's going to be some things in our universe that are so far away that we'll never see their light. They'll be moving away as the light's traveling towards us. And since the universe is expanding, it'll never reach us, which is kind of bothersome, but is also why we don't see a sky at night that's completely bright. So because there's a finite speed of light, things that are farther away than that, we can't see and we'll never see, which is kind of strange. We'll never know what's outside of the observable universe because of this finite speed. Right?
I feel like one day somebody's going to figure that out. Like,
Maybe, but what if we're just stuck? What if these are the rules and there's no other things, right? So the two equations we're going to use with this speed, we can still use the wave equation and we can still use the speed definition. Since light is a wave, I should be able to use the light wave equations. And what I would do is, let's say I'm solving a problem, right? I would take my speed of light and that gets replaced. That gets to replace v. So I would put in 3 times 10 to the 8th for v in either of those two equations to find my missing values. So if I do like a light going around the Earth, I would use the velocity distance time equation because I'm asking how long does it take for a time, so I'm finding t, knowing the distance is 40 million meters. and the speed is 3 times 10 to the 8th meters per second. So I'm going to take my speed as distance over time, and imagine I'm doing the show your work thing. So we're going to like write the equation, then substitute, then solve. V gets replaced with 3 times 10 to the 8th. D gets replaced by 40 million. And that gives a time of 0.3 seconds. So for all the human beings that currently live on the Earth, we can pretty much all talk to each other with things on the electromagnetic spectrum at functionally instantaneous, like that's functionally instantaneous speeds, right? But what if we were trying to talk to an astronaut that's stationed on the moon? One of the things that NASA wants to do in the next few years is reestablish studies on the moon. Not sure if we're going to reestablish like people stay there for a long time on the moon, but now the time delay starts to get bigger. If we had astronauts on the moon, it would take about 1.2 seconds for the light to get to them, or the radio wave of communication to get to them. And that's still not that big of a deal. Like a 1.2, if there was an emergency, you could like get a signal back to Earth pretty quick. But when you start getting anything away from the Earth and the moon, that becomes a problem, right? So this is Earth, Moon, Mars. Let's say there's a problem when we're flying the Ingenuity helicopter on Mars. It takes 3 minutes for the light to get back to Earth, or the radio wave or the X-ray, whatever signal that they're using. That's problematic, because that means, let's say they're flying the helicopter and they get an unknown problem, right? If it takes 3 minutes for the signal to get to Earth, then they talk about the problem and send a signal back. That's going to be like a 10-minute time delay. You can't have a normal conversation with a 10-minute time delay. Right? So even though the speed of light is fast, on a universe scale, it's really, really not. The distances outside of our planet are so big that the speed of light is actually kind of slow. The nearest star to us is about 4 light years away. So imagine instead of light going from Earth to Mars and taking this little amount of time to get across the screen, if it took 4 years for the light to get there, and it would take 4 more years for the light to get back, that starts to be a really big problem. Right. So on this slide, don't feel like you need to write everything down here. This is a recap. Because in the last unit, we talked about all these wave properties, and we know light is a wave. Light has to do all the same things. So, big list coming up. Because light is a wave, it has a source. The source gives it its frequency, amplitude, and period. Usually for light, the source is some sort of electron. Usually. It's an electron moving up and down. For gamma rays, which are much more powerful, that might be like a nuclear transition. So a proton moving into a more energetically stable state instead. But don't worry, some charged particle moves up and down, creates a wave. That wave doesn't actually need a medium. It has a wavelength, whether there's a medium or not. So it has a wavelength. It's got that speed we just talked about, really super fast speed, slows down if it gets into a medium. Right? And then it's got to do all its normal wave behaviors. So if regular waves can do these things, light should be able to do them too. Things like reflection and refraction, transmission and absorption, and what else we got? Scattering and diffraction. We've got interference, Doppler effect, and standing waves. All of those things that we talked about in the last unit are going to get repeated in this unit. Some of the ones that aren't going to be repeated in terrible depth. Standing waves make more sense with sound than light. You have seen standing waves of light. Those are lasers, right? Those are resonance of light creates lasers. Doppler effect, you hear more with sound than light. So that means we're going to spend a lot of time on like reflection, refraction, diffraction, and interference. So video time for a second. I'm going to stop this recording